Imagine taking a wildly complicated, messy signal, like a jagged sound wave, and shattering it into perfectly smooth, distinct pieces. Those clean pieces are infinite orthonormal series. They form the mathematical machinery that makes everything from signal processing to quantum mechanics actually work. By understanding the rules that govern these series, we gain the ability to decode the geometry of infinite dimensional spaces. Inner product spaces give us a way to measure geometry, specifically angles and lengths. Hilbert spaces add completeness, meaning the space has no holes where a limit might fall through. This animation shows a standard 3D coordinate system scaling up. An orthonormal sequence builds an infinite grid where every single axis is perfectly perpendicular to the rest, and every unit vector has a length of exactly 1. When we perform an orthogonal decomposition, we take an arbitrary vector and cast its shadow onto each of these infinite axes to measure exactly how much of it points in that specific direction. These perfectly rigid axes create a mathematical scaffolding. We use it to precisely measure and reconstruct any object in the space. To see this scaffolding in action, we can look at classic trigonometric Fourier series. The integral of cosine mt times cosine nt, evaluating to 0, means they act as perfectly perpendicular vectors. Multiplying the sum by basis vector ej, orthogonality forces mismatched terms to 0. They blow away, leaving exactly the coefficient we need. The inner product acts as a strict mathematical sieve. It effortlessly isolates exact Fourier coefficients, even in highly abstract spaces. We face a structural problem. If we add up an infinite number of these orthogonal vectors, how do we guarantee the total sum actually converges to something finite? This animation shows orthogonal vectors placed tip to tail. According to Theorem 3.52, this infinite staircase converges to a finite point if and only if the sum of squared coefficients converges. Those scalars must be the exact Fourier coefficients we calculated earlier. This pie chart represents the total squared length of a given vector x. Because of Bessel's inequality, as we add up the squares of its Fourier coefficients, the slices fill the pie but can mathematically never overflow it. The total energy of all these infinite orthogonal projections is strictly capped by the original length of the vector itself. So, if a series of Fourier coefficients always converges, does it guarantee that it perfectly reconstructs the original vector x? Not necessarily. The series only converges to a projection of x. It perfectly reconstructs the original vector only if our orthonormal sequence covers the entire space, a property we call being total. That brings up a counterintuitive edge case, covered in Lemma 3.5-3. What happens if our Hilbert space contains an uncountable family of orthogonal vectors? This diagram shows a vector of finite length. If we try to cast shadows onto uncountably many axes, geometry steps in. We cannot have infinitely many large projections without the sum of their squares eventually exceeding the vector's own total length. Regardless of how vast the infinite space is, any vector x is strictly limited to at most countably many non-zero Fourier coefficients. Treating functions as orthogonal vectors allows infinite orthogonal series to function as the heartbeat of Hilbert spaces. This infographic breaks down the 3 rules we've proven. First, the mathematical sieve isolates exact coefficients. Second, the infinite Pythagoras rule ensures convergence. And third, we have a strict countability limit for any vector's non-zero coefficients. Mastering these rules proves that complex Fourier analysis is ultimately a special case of abstract geometry. If you found this breakdown helpful, please like, subscribe, and share the video. It helps us keep bringing you complete explanations of advanced mathematics textbooks. Drop a comment below and tell us which theorem, proof, or chapter you want broken down next. See you in the next lesson.